We'll be starting in few minutes. Today it will be the review of the 11th and 12th week. Solve problems based on the theory there. Okay, so we start now. So this will be problem solving session on yeah, week 11 and week 12. This is the last session for this course. Okay, after that you'll have your exams. Okay. Okay, so let's get started. So there is the question is which of the following is correct for the subtask terminations in MAXQ function framework. Okay, so as always, I will go through the theory a bit so that you can get a better understanding of what is being told here. Okay, so starting with in MAXQ value function decomposition. So what we are doing is that given that learning the whole MDP is harder, okay? So we divide it into several smaller MDPs, okay? Which are the SMDP, semi-MDP formulation that we have seen before, okay? So that is what we do, okay? So dividing into several smaller MDPs is what we're doing here. Okay, so just I will take the class example, okay, and explain it better because we've been needing that. I think here is it is. Uh, so something like this, okay. So this is the diagram we have, okay, and so everything is there. I don't even need to draw, okay. So this is our root task, okay. So the problem statement is that you have a taxi and the passengers are at the location R, Y, G, P. Okay, so the taxi runs and picks up the passenger in only one of these four locations. The passenger is waiting at only one of these four locations and also will be dropped at only one of these four locations. Okay, and this shaded blocks, the dark shaded ones, are the uh, where there is obstacle. So The taxi cannot go through them, okay, or stay at them, or take that path, or whatever you say. So this is the problem statement we have here, and so the thing is that like if you reach to the correct destination, you get plus 5. If you pick up the person from at the right destination, then we you get plus 5, okay. And other things are also there, like you have to navigate up, down, left, and right. So this is a grid world problem. So there are only four possibilities of what you can do, okay. And so the navigate t here. So the t is a variable here, which represents which location the taxi will be going, okay. So the some of the possibilities here are that it picks up from the right location, okay, or another is it picks up from the wrong location. If it picks up from the wrong location, you get a penalty of minus 5, okay. If it drops off with the wrong location, you get a penalty of minus 5. If it means like strikes through one wall, then it get a penalty like that. Okay, so some reward, some penalty situation is there. Okay, so this is the problem statement we have, and this is the graph structure which represents what actions it can take. Okay, and okay, so so these are the like picking up, which can entail different actions to achieve that. Okay, like moving means uh, whenever it got the information that it needs to pick up at location, suppose uh, R, then it is at some say this block, okay. So you need to move forward, okay, which is right, okay, then top and then left, okay, and then pick up, okay. So this is composed of several smaller actions. So these pick up, down, left, right, put down, these are the primitive actions, and pick up, and this one like pick up one means like as a whole action, as a whole achievement, drop off, navigate. These are the macro actions, or like cumulative actions, you can say. Okay, so this is what we have here, and to formulate that, so this is the root MDP that we have to learn. So we are actually not doing that. What we're doing it, we're dividing into a several smaller MDPs. Each of them is actually a semi MDP. Okay, so the K MDPs here, semi MDPs, or you can say like subtask. Okay, the subtask we are trying to achieve. Subtask here can be like so here root MDP is like doing all the activities and leading to success. Okay, something like that, and and smaller MDPs is like smaller actions like pick up at R, pick up at G, drop at P, like that something. Okay, so this is it. Okay, and we define the each of the smaller MDP, smaller task, as SI, AI, RI dash. Okay, so this is the reward allocated with every subtask. This is called pseudo reward, and and this SI is the all the sub states that are available to that sub machine, or you can say the smaller task, subtask. Okay, these are the SIs here, and okay, so so if you reach the termination state of any of the sub machine, okay, it immediately exits, does not take any action, and it's moved to another state which is not inside the smaller machine. Okay, so this is the question we have here, okay, and it means that like subtask termination, okay, subtask to terminate in that phase, okay, so which is the one of the two correct options. So the subtask immediately terminates, which points to that in every situation it terminates immediately. So there is no stochasticity or probability attached with this action. It is actually a deterministic action, okay. It is always taken when you achieve the subtask that is desired to be achieved. So it is a deterministic task and it happens immediately. B is the correct option. So this is it. Okay, so moving on. Uh, so each of these subtasks, how do you represent that in the form of a rollout? Okay, this is SI, AI, and goes on like this until you get all the rewards. Okay, plus R. So So this Ri is the pseudo reward which is contained in each subtask, and R is the reward that you get at each for each action. Okay, or some of those rewards. Okay, say discounted reward or return. You can say. Okay, so this is what it is. Okay, and the transition probability is what we have seen before. Okay, S dash tau. Tau is the time for transition, and this is the action. Okay, for every smaller MTP. Okay. Next, so this is the reward, okay, and for a state transition S to S dash for with action A and taking extra time tau here, okay, it is equals to expectation over. Okay, this is this expected reward here. So this is the accumulation of rewards for each SMDP, okay, and so this is what we have written, okay. Mm, mm. Okay, so continuing, we have this value function for each SMDP in this MAXQ formulation. Okay, so the value function is V by IS. So I represents the action that we're going to take. Uh, So this is a state transition probability, and so this reward is nothing but this value function here. Okay, for a policy pi I for each MTP. Okay, it's each SMTP and given at a state S. Okay, plus you have this summation over this uh, transition probability for policy pi. Okay, into is multiplied by gamma to the power tau. Okay, that we have seen in the SMTP formulation. So the okay v pi into I comma s dash. Okay, this is what it is. Okay, um, this can also be written as the q function form, q pi I s a v pi a comma s plus summation s dash tau pi pi s dash tau s comma a. So this is it. Okay. Uh, so this is the value function at the start of the subtask A, and this is what we call the completion function. Okay, which is denoted by C pi I S A. Okay, so this is the cost or the reward at subtask I after at state S after completion of action A. Okay, this is what it is, and value function is the at the start of the action, which is like it has not accounted for the action. Okay, and C pi is the accumulated reward after taking action A. Okay, so this is how you define it. Moving on, so this is q pi I S A is equals to v pi s comma A plus C pi I S A. Okay, further this v pi A comma S, which is the value function up before taking action A up to that point. Okay, so that is equals to at state S. Okay, that is equals to q pi A S pi A S So, so this happens. This is the Q pi, okay, for a previous state A, previous action A. So if it is because if A is compound action, okay, and the next one happens, which is the expected reward in this case, okay, if A is a primitive action, okay. So we'll uh, keep doing it, okay, until A becomes a primitive action, okay. So that is our policy here, okay, and that is how we do it, perform these actions, okay. So I'll continue after this, after a small break, okay, and Okay, so continuing, so we have reached that for compound actions, this is the next course of action is the Q function, and using the policy with respect to the previous action uh, as the driving force. Okay, and if it is a primitive action, then we just take the expected reward. Okay, for each transition. So so the policies here can be from pi 1 to pi 2 to pi k for all the k smaller MTPs. Okay, and so when we start with a time t0, value function is t0 for state s is equals to c pi 0 s a1. So you have taken action 1. Okay, and so you can see that how we're formulating is that uh, so you're taking for each value function, what you're doing is taking this one, okay, which is this, okay, q, and which is equals to v pi plus c pi. Okay, c pi we have already written, so you have to write the v pi for action a1. Okay, a1 comma s. Next, what we're going to do is that for this value function you can break it down into c pi as a2 plus v pi a2s. Okay, so you continue like that. Okay, and you continue it until you reach a primitive state an, suppose, then you just take the expected reward for that action. Okay, so this is what we do. Okay, next, the second question. uh, so we move on to the next question. So the summary on the max q value function decomposition is done for now. Okay, okay, so next what we have is that in max q learning we have a we have a um, question is in MAXQ learning we have a collection of SMDP. That's correct. In conventional value function the only argument was state. Okay, in MAXQ learning the function decomposition we have value function of the v, is or pi is the policy, and s is the state. What is I supposed to be in the above rotation? So what does I mean here? Okay, that is the question we have here. So it means the number of iterations. Okay, uh, for each updates. Okay, sorry, I here is the identity of the subtask or SMTP. So so as you can see here, so we will start with I here. Okay, I is the 0, so for the 0th SMTP we're doing it. Okay, uh, and that is what we're doing. Mhm. And we will continue until we complete the task. Okay, this is the answer. Okay, next is what we have already done here, and I've explained to you. So this is the problem we have. Which of the following are the primitive actors? Primitive actions are these ones. Okay, so what we have in options is left. Okay, so left is primitive, drop off is not primitive, navigate is not primitive, put down is primitive. Okay, so these are two options. Okay, 1 and 4, C is the answer. Okay, easy. From the discussion in the class, it said that navigate is not a simple subtask. What is a parameter t in the navigate t from the class discussion? Okay, so the t represents which destination we are going to go. According to that, a different SMDP will be formed. Okay, so it is this answer C. Okay, this is done. Next, state true or false. So order of the above cell graph is important. Subtask should be performed via this ordering. So ordering is not important. Order is just for representation. Um, you should take actions which are most optimal. Okay, which is optimal. Okay, and this is the answer. Okay, and next what we have, suppose the passenger is always either inside the taxi or in one of the four uh, pick up or drop off. Okay, location. This means there are five states for the best passenger location. And for the given taxi world, what is the number of states that suffice to define all information? So the number of states that we have, okay, so that we can define everything, okay. So we'll go here, okay, and you can see how many boxes are here total, okay. So which box currently the taxi is at, we need to know that, okay. So for that, what we're going to do is like, so these are 25. So 25 total boxes are there, out of which how many boxes are available to the taxi is just, you have to subtract this 4 and 3, 5, 4 and 3, 8. Okay, 1, 2, 3, 4, 5, 6, 7, 7. So these are the 7. So the total 18 boxes are available. Okay, for the taxi. Okay, so that information we need to define which state of the problem we are in currently at, and also the state of the, so the state of the taxi has been defined by 18 boxes, but the state of the person is still to be defined. Okay, if the person is outside and still to take the taxi or will get off the taxi, there are four possibilities total. So these are four. And okay, and so the four possibilities of the passenger uh, being there, and five is that it can stay at one of the four location, also be on the taxi. Okay, so that is five like that. Okay, this is the answer. Okay. Now, four is one of the location at which the drop or pickup has to happen for that situation. Okay, for that SMDP. Okay, that is four. Okay, five is where the person is. 18 is the number of boxes available to the taxi. Okay, that is how we get 18, 5, and 4. So multiply these together, you'll have all the states possible, states that are required. Okay, this question is done. Question number 6. Next, we move on to option discovery. Okay, and so the question is that state true or false. Okay, so bottlenecks are useful surrogative measures for option discovery. So, so that is what we have to see. Okay, so what is option discovery first? So options we have studied previously are which which state transitions are required to be known. So the state two means the several state transitions form an options, okay, to required and to reach in a required state, okay, and so that is called options. Okay, there are two type of options like Markov options and semi Markov options. This we have seen. Okay, next is that. So why do we need option discovery? So we need option discovery so that we can reduce the state space we have, okay, and we can solve this problem easier way, okay. So you define that option between two bottlenecks actually occur between the start and the next bottleneck and the first bottleneck, okay. So that is how you define it, okay. So that is why both bottlenecks are useful, okay. And why first of all we'll start with what is means why do we need to have option discovery. Okay, so it happens in reusability, helps in reusability, cuts down on exploration, cuts down on exploration. So you don't have to explore more because for that smaller part you can use SMTP without any caring for the bigger problem. And you have transfer learning. So what you've learned in one SMTP you can transfer that. We've already seen these, okay. So the bottlenecks are important. So bottleneck is what like a lot of the is one of the states where a lot more states are connected. Okay, that is the bottleneck defined here. Okay, and so given that bottlenecks, we can define an options between two bottlenecks. Okay, and we can model the MDP as a graph. Okay, and we can use so we'll separate using graph cuts. Okay, and each uh, finding the weaker connections, okay, where actions may not be taken, and define the bottleneck according to that. So the first way to option discovery is graph partition. So another way to do for option discovery is diverse density. Okay, so what we do is that like there are several trajectories to solve the MDP. Some may not get to the solution as well. Maybe it is stuck in the bottleneck, or some may be just terminated because it was taking too much time. Okay, but so what we do that the number of trajectories passing through a state, that state may be defined as a uh, bottleneck. Okay, this is what we do. Number three is betweenness. So if node is connected to more shortest path, then select that node as the what do you call that option. We call that as a bottleneck. Okay, take that as a bottleneck. Okay, so bottlenecks are useful surrogate measures for option discovery that help in option discovery. So that is true. Okay, so which are these good options in hierarchical RL? So these are all the three we have seen before. A, B, C. Okay, so this one is done. Next to question number 9. Okay, so we define the action value for max q as this. Okay, we have seen that before as well. where QISA can be interpreted expected return when you are in subtask I and state S and decide to perform subtask A. Okay, so that is what you're doing. Assume that in taking A you get reward R1, and after completion of A you get reward R2 in completing subtask I, which is the current value of C pi ISA from the following. So in this, like for this formulation, you're starting with the subtask I and finishing with subtask A. Okay, so the reward in you get with finishing subtask I is R2. So that is this one. Okay, so this is the transition completion reward that you get. Okay, and this is the answer. Okay, any doubt at this? Move on to question number 10. Okay, three. Okay, question number 10 is here. Okay, and so let's make it move forward. In MAXQ approach to solving a problem, suppose that subtask I invokes subtask J. So the first task is MI, then it invokes MJ. Do the pseudo rewards of MJ have an effect on the subtask I? So the pseudo rewards of MJ that you have doesn't have effect on subtask MI. So it does have actually. So it does not have directly any effect, but the 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 policy that you learn for MJ will have a impact on the subtask MI. Okay, so that is because in the policy learning phase you'll have uh, the pseudo reward having influence on the policy learning. Okay, that policy will impact the MI. Okay, so that is why it is important. So I think I missed two problems here. Okay, so let me have that first. So these are the two problems we have. Okay, first, then you'll have go to the question number three here. So we are in an environment in which the agent is randomly dropping. So this week number 11 is done. So moving on to week 12, which is on partially observed MDPs. Okay, and so we begin the discussion on that. And so consider an environment in which an agent is randomly dropped into state either S1 or S2 with equal probability. So what you have is, so you have this able to write uh, mm, so let's try this one. So this state to S1 and S2, so both two states are there, and agent is randomly dropped into one of these. Okay, with equal probability. So you're getting this with half probability, and you're getting this with half probability. Agent can only view obstacles present to the north, south, east, or west. Okay, so this north, south, east, or west, you cannot look far. Okay, so this is the This is a question of partially observed MDP. That is what we can understand. It does not know the full state space. Okay. However, the observation made in each direction by the agent may be wrong with the probability 0.1. So there is a probability that the observation it makes, okay, which it only can view the immediate ones, can be wrong by probability 0.1, but can be right probability 0.9. Okay. If in state S1 obstacles are made to the at present to the north, so what you are saying that for state S1 the obstacles are present at north and south, so that is what it has seen. Okay. And in the S2 it is present in east or west. Okay, so this is the problem statement we have. So these are where places where the obstacles is there. What is the probability of the agent being in state S1? Okay, so we have to find the probability of being in agent in state S1 if the observation made in that is that there are obstacles present to the north and west. So this is what we're given. Okay, so let us consider this, that the obstacles are present uh, to the north and west. Okay. Okay, and so that is what we consider here. Okay, so this is what we consider as B. Is gone. Okay, so this is B for us. Okay, and the probability that agent is in state S1 is A. Okay, so this is BA given B. Okay, so this you can calculate as B. So you will use the Bayes theorem here. So first let us understand what is the probability of being in state S1. Okay, given that the obstacles are in north and west. Okay, so this is the problem statement we have. Okay, so we have observed that that obstacles are in this is given that this one is correct, so these two are correct. Okay, okay, and so it is given that these are wrong. Okay, these are wrong with probability 0.1 and these are correct with probability 0.9. Okay, so this is the problem statement we have, and so the probability of occurrence of S1 given that this is what we have. Okay, so according to Bayes theorem, what we have is we can write it like this, and we have the evidence term at the base. Okay, so occurrence of A or B. Okay, or means A or not A. Okay, not A means occurrence of S1, not A means occurrence of S2. Okay, and so this becomes B A. So you add for the all the summation. I mean, this is like basically what you call that is like integrating over A, summing up over A. And this is B given not A, and and A not A. Okay, so this is what we have. So probability of occurrence of A is half. Okay, and not A is also half. So these two you can ignore and simplify as B given A, B given A, and B given A plus B B given A naught. Okay. So B is that the obstacles are present at north and west given S1 has occurred. So what is the probability of that? That is not too tough actually. So as you can see, so given this has occurred, so S1 is there, okay? And what you need to know is that this is 0.9 and 0.1. So these two should happen simultaneously uh, so that we can get our answer. Or is it correct? Or you can say that like occurrence of north is 0.9 and so occurrence of west is 0.1. Okay, because according to the observation of S1 the west should not occur, but it has occurred. Okay, okay, so that is what we do here. 0.9 into 0.1 divided by 0.9 into 0.1 plus what we have is that so it the north occurrence of north should be 0.1 here and west is 0.9, so that is what we do. Okay, so what does it become? This you can eliminate this, so become 1 by 2 and 1 by 2 is our answer. Okay, B. Okay, so using Bayes theorem we can solve this easily. Next, move to question number 2. So this is the question we have, and so S1 has obstacles only to the north or south. Okay, so S1 has at north or south, and S2 has east or west. This is the problem statement we have. What is the probability of the agent being in S1 if the so the same formulation, okay, and the probability of occurrence of both of S1 and S2 is still half, so it simplifies to B given A and divided by B given A plus B given A naught. Okay, so this is the we have. Okay, so for S1, for this one what we get, S1 is there. Okay, that's good. And then what we have, the occurrence of the required north, east and west should be there. Okay, so occurrence of north is 0.9, east is not occurring, but we have to make it occur, so that's 0.1, and west is also not occurring, so we have to make it occur, so 0.1 divided by the same thing, because next so we have this one. Okay, and here what we have to do is for this state, okay, for S2 it is present in only east and west. Okay, so east and west 0.9, okay, but other is 0.1, this is 0.1 and 0.9, 0.9. So all 0 point are gone. Okay, multiplied by 1000, that is what I mean. Okay, so what we get is 9 by 9 into 81. Okay, so this becomes 9 by, so this becomes 90. Correct here. So the top becomes 9 and next what becomes is 81 plus 9 is, do we need to see something else here? At only north, east and west, so only these things are there, so other is it should not occur. Okay, so like the south one should not occur, so but it is occurring, so we have to make it 0.1. Okay, so this will be same here, 0.1, and here it will be 0.1, 0.9, 0.9 and For the south part, it is not occurring, and we have to keep it like that. It is 0.9 only. This is what we get. Multiplied by 10 to the power 4. What we get is 9 by 9 plus 93729. Okay, so divide by 9 here. 1 plus 81. 1 plus 82. This is what we get. Previous one we have to correct this one. We have got it wrong. So at only at north and south, north and west is there. So west is this. Okay, east is 0.1 and south is 0.1 here. Okay, so you multiply and get 9, divide by 9 plus, next what you get is north and west. So west gets 0.9, north gets 0.1, east gets 0.1, and east gets 0.9 and south gets 0.1. So multiply 10 to the power 4 and this becomes 81. North and west is there. So west gets 0.9, north gets 0.1, east get not occurrence of east. Okay, so that gets 0.1, and then south not occurrence of that 0.1. 81. 1 by 9. It's maybe a little wrong, I don't know. Achha, no, this is correct. Okay, so, we are not, this is not the only situation. Okay, we are considering only means like that obstacles are present in north and west. It is not like that it should not be present at other situation. It can be present, may not be present, whatever it is, we don't care. Okay. Okay. So continuing, what we have is question number 3. One of the reasons that history-based methods are not feasible in ways because of the significant increase in the state space and state space size when the trajectory is long. That is correct. When the states, number of the states increases polynomially with respect to trajectory and length. No, it increases exponentially. Okay, so C is correct. So this is what we get. In case of POMDPs, which of the following is a good estimate of the return of a trajectory of a policy pi? Given the current belief state and solution to understanding and MDP, so which of the following is a good estimate of the return? Okay. So weighted average of V pi, where Vs are the weights, the belief states are the weights, and the weighted average of the V pi is what we get as the uh, good estimate of the return. Okay, so that is what we do here. Next question is this one. So this is the first order Markov system. Why? Because given this state, okay, we can completely define the another one. Okay, given this state, I can define one. Just give one adjoining one, you can define the next one. Okay, that is what we need. Given this one, I can define this one. Okay, given this one, I can define this one. First order Markov system, and so it automatically becomes second order, third order, fourth order, because given one of the states you can move 4 steps, 3 steps, or whatever. Okay, so it's very easy like that. This is all of these are correct. Okay, this is done. Okay, so this is the problem we have. Okay, so this are all solved now. So do you have any doubt here? No doubt. Okay, okay, let's finish it here.